This section begins our chapter on vectors. Vectors are quantities that involve both a magnitude and a direction. If they involve a quantity but no direction, they're called scalar quantities or scalars. Okay? A vector is basically like, you could call it an array in a way. It has a magnitude or a length and a direction or an angle. A scalar is just a number, any number. So a line segment to which a direction has been assigned is called a directed line segment. We call P the initial point and Q the terminal point, and denote it by ray PQ. The magnitude of the directed line segment is its length. So the magnitude is the length from P to Q. And we denote that with these double bars. Geometrically, a vector is a directed line segment. So it's a line segment, but it's got a direction. So that's why on top we are denoting as a ray. But it doesn't continue forever and ever. It does end, but it has a direction. So that's why it's got an arrow. So when you draw vectors, you have to make sure that you put the arrow on it, so we know which direction you're going in. When we represent vectors, we either make them very, very dark, like bold, like this, or you can make them with a little ray on top. And the magnitude is the same, only with the double bars. In general, vectors are equal if they have the same magnitude and the same direction. So the first example here, these have the same length, the same magnitude, and the same direction, so they are equal. In picture B, they have the same length, but they're not going in the same direction. They're slightly different, so they are not equal. C, they have the same length, but they're going in opposite directions, so not equal. And D, they're going in the same direction, but they don't have the same length or magnitude, so again, not equal. For example 1, it says show that U equals V. To do this, we have to show that they have the same magnitude and the same direction. So first we'll show that they have the same magnitude. And we do that by basically using the distance formula. So for vector U, that's the one on the left, we've got let's see, I did the y values first. It really doesn't matter, but the y values subtracted squared plus the x values subtracted and squared. So that would give us the square root of 16 plus 9. 6 minus 2 is 4. 4 squared is 16. And then negative 2 plus 5 is 3. 3 squared is 9. That gives us the square root of 25, which is 5. And then we want to find the magnitude of V. So subtract our y values, square, plus subtract the x values, square. And you may be saying, well, don't you start with the x values? Yeah, you usually do. That's just the way I did this time. But it really doesn't matter because we're adding in between. So, okay, so we got the square root of 16. 6 minus 2 is 4. 4 squared is 16. 5 minus 2 is 3. 3 squared is 9. Finnick, my goodness, it is dark. You're not going outside. Excuse me. Excuse him. Okay, square root of 25 is 5. Next, we have to show that they have the same direction. Now, how do we do that? Well, these two lines would be heading in the same direction if they have the same slope, the same rise over run. So we're just going to look at the slope. So the slope of vector u would be subtract the y's over subtract the x's. That's 4/3. And the direction of vector v, the slope, would be subtract the y's over subtract the x's, also 4/3. So we have verified that these two vectors have the same magnitude and the same direction. Therefore, we can say that vector u is equal to vector v. Example 2 asks us to sketch u plus v by placing the initial of v, vector v, at the terminal point of vector u. So basically what we're going to do is, I'm just going to do this the easy way. I'm tracing over v and then selecting it and moving it. Basically, you could count up 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5, 6, and that would do it. Connect your endpoints there. So there is v, and so u plus v would be starting at the beginning of u and ending at v. This is u plus v. Next, we want to sketch v minus w by drawing v and w with the same initial point. Okay, so we've got v already drawn, and I'm just going to move w up to the same initial point of v. We could move v down. It doesn't really matter, but I'm going to move w. And I can see that w is drawn 4 down and 2 to the right. So I'm going to do the same thing here. And that should be w. Now, this time we want v minus w. Now notice when we were adding, we started from the initial point of v and went to the terminal point of u. When we're subtracting, we're going to start with the terminal point of w, the second one, and go to the terminal point of v. So instead of going initial to terminal, we're going terminal to terminal. And that is v minus w. Then in part C, it says sketch negative 2v and 3w in standard position. Well, standard position is starting from the origin. So I'm going to start by sketching w here in the origin. And it says 3w. So we're just going to take it and go 3 times as long. So 1, 2, 3, And so all that will be 3W. And then it asks for negative 2V. So what we do is we'll take V, and it's, let's see, up 3 over 2. But notice how it's going down to the left. To sketch negative, then it needs to go up to the right. That just changes direction 180 degrees. Okay, and so 2V would just be taking that 1, 2, like that, negative 2V. We've got some definitions and properties here that we'll look at more in future sections. So scalar multiplication is what we just did here, where we're multiplying a vector by a scalar. And scalar is just a number, any constant. Negative, positive, fraction, decimal, any constant. The sum of two vectors, denoted u plus v, if you've got vectors u and v, is just the two vectors added. So if you want to find the sum of two vectors, you take, if it's u plus v, then you take u, place v's initial vector or initial point at the terminal point of vector u, and u plus v is this vector from the initial point of u to the terminal point of v. U minus v is essentially the same thing as v minus u is essentially the same thing as v plus negative u. So if we have v and we graph negative u, so negative u would start at the terminal point of v, and then u, or v minus u, would be from the initial point of v to the terminal point of u. A zero vector is a vector whose magnitude is 0. It has no length and no direction. It's basically just a point, I suppose. Properties of vector addition. Properties of addition are the same for vectors. So the commutative property, u plus v, is the same as v plus u. The associative, u plus v plus w, is the same as u plus v plus w. The additive property, if you add 0, you get back the same thing. If you subtract a number, then, or its opposite, then you get 0. For multiplication, same properties apply as we've always had. If you take two scalars, c and d, and multiply them by u, then it's the same thing as taking d times u and then multiplying times c. Distributive property holds. C times u plus v would be cu plus cv. And c plus d, if you've got two scalars and multiplying by one vector, would be the same as cu plus du. 1 is still the multiplicative identity. If you multiply by 1, you get back the same thing. If you multiply by 0, you get 0. And the magnitude property, this one, if you're finding the magnitude of CV, that's the same thing as the absolute value of your scalar times the magnitude of V. And we'll go forward in a new video.